This video demonstrates how to accelerate the training of a neural network in PyTorch on a GPU by using multiple CPU cores for the data loading. Let's SSH to a Droid and install PyTorch using Conda. If you happen to be off campus, then be sure to connect via VPN. The environment will be stored in your home directory. Make sure you have enough space by running the check quota command. Next, we'll download the MNIST dataset. Let's move to Scratch Network for this work. Let's git clone the example job repo and run a script to download the data. It's downloading now. Just a moment. Let's take a quick look at our PyTorch script. Okay, looks like a standard script. Let's keep looking. The script trains a CNN on the MNIST dataset. Num workers is 1 by default. In a moment we will try varying num workers. Be sure to enter your username in the Slurm script. Next, we submit the job and examine the GPU utilization. The utilization is seen to fluctuate around about 18%. Note that the recording has been sped up. The actual time was 42 seconds. The output looks good with an accuracy of 99% on the test set. Our baseline case took 42 seconds to run with a mean utilization of approximately 18%. In this case, the GPU is not being used effectively. This is probably because it is not being fed data at a sufficiently fast rate. We will return to this in a moment. The next step is to install line profilers so that we can examine the performance of each line of the train function. This can be done using the conda install command. We add the profile decorator as described on the Research Computing webpage. The Slurm script needs to be changed so that kernprof is called instead of Python. Let's submit the job and examine the GPU utilization. It appears that the utilization is slightly lower by a few percent. The profiler comes with an overhead penalty which caused a slight slowdown of the code. In general, line profiler is lightweight and such penalties are not significant. It is an excellent tool as we will see in a minute, and you should use it for your Python projects. Now that the train function has been profiled, let's look at the results. First, let's rename the file so that we can return to it later. About 38 seconds of the 45-second runtime was spent in the train function. We see that 83.6% of the time within the train function was spent on line 42 where the training data is loaded. This is somewhat surprising. One might have guessed that the forward pass or the calculation of the gradients would have been the most expensive operation, but that was not the case. PyTorch can use multiple CPU cores to accelerate data loading. Let's try using 2 CPU cores and 2 workers. We submit the job and look at the GPU utilization. The average value is now around 23%, which is an improvement. Let's look at the execution time. Very nice. The code now runs in only 28 seconds. A substantial improvement. Let's keep going by trying 4 CPU cores and 4 workers. The utilization is even higher in this case. The execution time has been reduced to only 19 seconds. The code is already running more than twice as fast, but let's keep going by trying 8 CPU cores and workers. 8 cores is right. 8 again. The utilization is even higher. This is a clear indication that the GPU is being fed data at a faster rate. This case leads to an execution time of 15 seconds and a mean utilization of around 55%. This is much better. Here are a few more results. When the profiler is turned off, we get a slight improvement in performance. We tried 8 CPU cores and 4 workers, but that was not our best run. Lastly, as a test, we tried 8 cores and 1 worker, and as expected the performance was poor. Let's now compare the profiling results for the case of 8 CPU cores with the original case of 1. We see the dramatic decrease in the amount of time spent in the train function. The data loading step with 8 CPU cores has been reduced to 18% from 83.6% in the original case. The new slowest line in the case with 8 CPU cores is optimizer.step, where the weights are updated. Maybe using a different optimizer would improve the performance even more? It is important to realize that MNIST is included as part of the PyTorch dataset module. You will need to write a custom dataset class for your own work. This is explained in the video by the user known as Python Engineer on YouTube. The link is in the description to this video. Now that spring has arrived, we can look back on these snowy images of campus. So, what did we learn? We saw that it was not enough to simply install PyTorch and train the network using only a single CPU core. The line profiler tool was used to identify the bottleneck, which was found to be data loading. By using multiple cores, we were able to boost the overall performance of the code by almost a factor of 3. When you try this with your own code, you will need to write a custom data set class. The good news is that soon every research computing cluster will have GPUs. With the release of the new A100 GPU, the lessons in this video are more important than ever, since very high data transfer rates are needed to keep the A100 busy.